Hi guys, and this is the last part of lecture number 2. We'll be here speaking about the loss, the delay, and the throughput of the transmission of a packet in a link. Okay, so there you go. Remember, when we in the internet we mostly use packet switching, right? Packet transmission from one side of the link to the other side of the link. That we'll be now talking about client and servers. So the client is the one receiving the packets. The server is the one sending the packets. Yes. So as to remember, here we have okay. As to remember, here we have our main switch. Our main switch that keeps our packets, right? And we have the following one. So you can see that this little packet, it's coming here to find a queue. They are packets there are packets that were there before it, right? So that's basically one reason why we can have a delay, because they are already there's already a queue and a new packet is coming, and then you'll find a queue. So this is on first come first serve basis, and there will be a little delay. Yeah, cool. So there are multiple reasons why a delay can happen in a network, like, but we mostly have 4 of them. Like the very first one we mentioned, it's at the node, the queuing one. So we can have multiple items in a queue, right? So that can be a problem. We have a nodal processing. How long does it take to process a particular packet in a packet switch, right? We have the transmission, like it's been processed. How long does it take to basically send that one out, right? Like from the nodal processing, it gets into the packet, it gets processed into the packet, and then how long time does it take to leave the it gets processed into the switch, how long time does it take to leave the switch. Now we have the propagation, which is a physics problem. So how long does it take to travel from the switch to the next network component? It can be the destination, it can be another switch, another network component. So the simple formula we have to calculate all the delays, right, is basically as follows. We have the propagation, you have the transmission, you have the queue, and then you have the processing, right? This one gives you the overall delay of a particular packet when it travels at a particular node. That's the delay at a particular node, and we call a node like a network entity. It can be a switch, it can be a router, it can be a computer, it can be any network device. Alright, so the processing, the nodal processing. What happens when we have a nodal processing issue? So you can check for bits error, because like when a packet arrives, then we have to check everything. Remember that it needs to go to a routing table. It can have some errors into the packet, then it has to deal with it very first time. Now we now need to remember, we need to know what is the next link. I mean, all of this processing happening and all those stuff. Who are you? What do you have? Why are you going to? These type of things that the switch is asking the packet coming, and then they say it's very less than some milliseconds. That's not much of a worry. Now we have the queue. As you know, when you go to any company where you need to have process like in a bank or something, then if you go to the bank, for instance, and then you want a statement, and then there's no queue, boom, you will get your statement. But then if there's a queue, and then per person, it takes 2 seconds to, like, you go to the bank. Let me put the stylus here instead. So you go to the bank, and then there's no queue, and the processing time is 5 seconds. The processing time. Then in 5 seconds, you get your statement. Fair enough. Now, I get rid of this. Now, if you go to the bank, and then there are 5 people in a queue, right? And then it takes 5 seconds to process a single person, then it will take 25 seconds in average for you to process your bank statement. This is the queuing stuff that happens as well. So it depends on the congestion level of the router. Here it depends on the congestion level at the bank. Okay. Now we have the transmission delay, right? So how long does it take for your data to leave, like to basically be processed and all those things? So you have the length of the packet, like the size of the packet. You have the transmission rate of the channel, which is given in bits per second and all its multiples. And then you can have the transmission delay, right? And after that, you have the propagation delay, which is basically the one you know very well. I mean, so you have the length of the the, the, the the link, and then you have the speed of the link. If you remember, your velocity, it's equals to the distance divided by the time, right? But then what we want the time. So if you want the time, then what we do, we multiply. Yeah, so we basically, because I just don't want to take shortcuts, because what I would do, I'll bring t up here, I'll bring v down here, so the time will be equal to the distance divided by the velocity, right? Which is exactly what we have here. So we have our distance divided by the velocity, and the velocity, they decided to call it s, so it's the same process. And as you know, the fiber is pretty quick. It means that with the fiber it will go faster than any other material. Okay, so please do not get confused. Those velocities, those transmissions here are very largely different, because they deal about different components, they deal about different units, so they are very different. Please do not mix those ones up. Now we will take an analogy of the processing time, the whole delay with a caravan and cars on it. Let's assume that a caravan, this thing, can hold 10 cars. So basically you have a 10 bits package, right? And you have now the booth, which is the router. So basically you have a set of data coming to the router, you have a set of bits into the caravan, you have the router, and then you have the link going off for the next router. So like the car propagates at, remember that we have we have the time, the propagation time, which is equals to the distance divided by the velocity, right? This is what we know. And we have the two, and then we have no, let's just leave it like that. So cars propagate at 100 kilometers per hour, right? This is the velocity. And then the tool booth takes 12 seconds to service the car. So the processing time is 12 seconds, right? Here is an analogy. The car is similar to a bit. The caravan is similar to a packet. How long time until the caravan is lined up before the second tool booth, right? So what we have here, for instance, is like if we have the entire caravan, right, the whole of it, right, like right here, since you have 10 cars, right, each car is having a processing time of 12 seconds, then we have 120 seconds, right? So what should happen is basically that's basically each and every car, or let's say the last car, will wait for the 9 previous cars to happen before that one gets processed, right? But then now, what happens for the entire caravan to finish, right? For the entire caravan to finish, then, and to the second booth, then what we have basically the distance, which is 100 kilometers per hour, right? Like all the cars are done, the caravan is being lined up, all the cars are done. So, and then they're going to the second booth. How long will it take, right? So we have 100, which is, this is the formula we'll be using. So we have 100 kilometers divided by 100 kilometers per hour. That's our velocity. Like this is in kilometers, this is in kilometers, this is kilometer per hour. Then we have 1 hour for the whole process to happen. But remember that the delay is equals to the sum of the other delays, alright? So what we have, remember the previous delays we were having, and this delay, what does it mean? It means 2 minutes. So the entire delay for the whole caravan to happen and to get to the second booth, it's basically 62 minutes, or 1 hour and 2 minutes, right? So this is exactly the entire processing time from the time that the caravan is full until the last car gets to the tool booth. So this is it. So you have your formula that you need to keep in mind about how long time does it take for a whole file with these bits, right, to leave from one side to the other side. Alright, and then we'll write about that. Cool. Let me clear this one up and let's go to the next one. Suppose now that the car are traveling at 1000 kilometers per hour, and suppose that the toll booth now takes 1 minute to a car, 1 minute to service a car. Will cars arrive to the second booth before all car service at the first one? So yeah, but then how, like, why, right? So let's calculate that one. We have our velocity, no, not the velocity, we have the time, which is equals to the distance divided by the velocity, right? Now the distance is still 100 kilometers, right? And then we have the speed. This is 100 kilometers. We have the speed, which is 1000 kilometers per hour, right? That is 0.1 hour. And yeah, you can basically compute that 0.1 hour, which basically, so since 1 hour is equals to 60 seconds, then 0.1 is equals to 0.1 hour is equals to 0. Is equals to 1 hour is equals to 60 minutes. So 0.1 hour is equals to 6 minutes, right? It's equal to 6 minutes. Now the processing time is 1 minute. Then we have 7 minutes. We have 7 minutes for the first car to arrive to the booth, right? And some of the cars will be still processing, and that makes sense. So you just have to use your formula and a bit of common sense for you to understand what's going on. Okay, now we have basically the packet queuing delay. What you need to understand is like when the packet length, right, is equals to, it's slightly equal to the transmission rate, then obviously the delay will be very, very, very long. It's like in mathematics, if you saw the limits, then this one goes close to it, to infinity, right? So when there is no, when the length basically of the packet in bits, it's smaller, it's way smaller than the transmission rate, then the queuing time is very small. An example, so you have the transmission rate, you have a transmission rate of 100 megabits per second, right? And then you have this is the transmission rate, right? And then you have L, which is let's say 1 kilobit per second, right? And this one, it's way smaller than the 100 megabits per second, like way smaller. So even if we have multiple of if we have multiple packets of this size, it will always go faster. So there won't be any worries with that. Okay, now if we have um, 100 megabits per second uh, transfer rate, and then we have a packet size of 100 megabits, then the queuing delay will end up being large, right? Because the processing time will be close to 1. It will be literally close to 1, and that won't be good. So it can be, the packet queuing can take long. Okay, now if we have the packet size which is larger than the transmission rate, that will take forever. And an example that I can basically tell you, let's assume that you have your MP3, you have an MP3 of 10 megabits, or yeah, you have your MP3 of 10 megabits. Now you have your transmission rate, like your download rate, for example. Let's say your MP3 is up to the cloud, and then you want to download that MP3. Not even an MP3. MP3 is too small. You have a movie which is basically 3 gigs, 3 gigabits, for instance, and then you're downloading it legally from internet, and you have your downloading rate, your transmission rate, which is, I don't know, 500 kilobits, it will take very, very long. Remember that 3 giga, it's 3 times 10 to the power 9. Yeah, so this is the file, and this is the file. Oh, this is the transmission rate. It will take a lot of time for you to download that file to your computer. It will take time. Cool. Yeah, so you have the similarities here, where if you are alone in a very, very, very large road, then you can just speed there whatever at whatever speed you want. But then if the road is congested more than what it's supposed to carry, then the delay time will be higher. All right. Now we have the trace route. Trace route. Very, very, very important concept in networking, and I'm sure you will enjoy that as soon as you understand how it works. So the trace route is basically a program that will tell you how many hops and how long time does it take from your computer, or from one computer to a destination computer, through the different uh, switches, right? So what happens, let me just do that. What happens is, like, this is the server, this is the client, but what I want is, like, how long does it take? How long does it take to send a request from this computer to this computer, and how many routers does it cross? Does he or she crosses? Does he or she cross to get the information? And what it does that 3 times per router, per router. So very first router, it will basically give you 3 different timing of, like, okay, I went to that router 3 times, and these are the different transmission time that I went through. It will do the same thing for the second router, go back to the first again and go back to the server, and do that for each and every single one until it gets to the destination. And it's okay, cool, we got to the destination, and then we came back with this amount of time. So here you have an example of the trace route from the University of Massachusetts until a website located somewhere in France. So what it does is, like, okay, the University of Massachusetts, it's located somewhere in, like, in this IP address. That's exactly the IP address of the requesting computer. And you have the 3 delays, the 3 delays time that have been recorded by the basically the whole procedure of the trace route, right? Because a packet goes and comes back with some delay timing. Now it goes to another router. Now the request went outside the computer, and then we have some more delays. And as we go on, then the trace route will eventually land in France. The trace route will eventually land in France, and then we'll be having the result going on. Okay, so so now what I've done so far, I was able to do the same thing, but then in a South African point of view, right? So in the South African point of view, we were able to, sorry, I don't even know how to remove. Okay, I think we'll just carry on with this. Okay, so in the South African point of view, I decided to look for the VITS website. Yeah, so VITS. So what happens is, it was like, this is my address, my my IP address, which is the local host address, and this is another IP address happening. This is my internet service provider. Cool ideas. And guess what? We have the internet. Uh, we have the internet exchange point from Johannesburg. The GINX, it goes there, and then it goes to the academic, or to the some sort of VETS internet provider. You can see this AC. It's for academics, um, uh, academic domains, and then it will eventually arrive to VETS, right? That's very impressive. I didn't show you the last part. The last parts were just three stars. Okay, now I wanted to go outside to trace the trace route from my computer to the Japanese government website. Obviously, they won't give me their their base IP address. That won't be very secure. But then the IP traveled down to Japan, and you would see that, cool, it lives in my house, is going back to the internet service provider, is crossing some IP addresses, I don't know which ones. These Kojangco are multinational um, internet service providers. They are located in the US for some reason, and then it goes to the UK, and then it goes back to the US, and then this IIG is we already in Japan, and it goes down to the website that I want. Hopefully it's even that, but I'm not sure it's that. Otherwise it wouldn't be secure. Cool. Yeah. So now we're speaking about packet loss. We don't worry, we are about to end. We are about to end this lecture. So the packet loss has, like, we saw that it has multiple reasons. It can be transmission delays, it can be queuing delays, and all those stuff. But then we have the link as well that can be a trouble for our packet, for basically either losing data or having very hectic delays. So we spoke about that earlier. Remember when we were talking about a queue being full, or a queue being yeah, if a queue is full, either the packet will get dropped, or the processing will get delayed and stuff like that. That's basically what happens. All right. So for the throughput, this is basically the amount of data going from one side to the other side, from the client to the server, from the server to the the router, from the router to the client. Right. So basics here, we have to mention that we have the transmission rate of the server, we'll call it RS, right? Now we have the transmission rate of the client, we'll call it RC. Now the throughput is the rate at which we're sending the data from one server to the client, to the router, to the server to the router, stuff like that. The instantaneous rate at any given, like the instantaneous throughput is the rate at any given time, like at a particular point of time, that's the throughput of your transmission. Now the average throughput is over a longer period of time. When you're doing a download or stuff like that, that's basically your throughput average time. Right, so take the links as some pipes, and pipes that have different sizes, shape and sizes. So not all the links between network component will have the same size. They will not have the same size, and if they do not have the same size, they will either transmit the same amount of data or they will become a bottleneck, right? So take a fluid for instance. If you have let's say a bucket here, you have a bucket here, and then you have let's say a pipe here, and then you have a bigger pipe here. Okay, so the rate at which the bucket will be filled, it will be only by the size of this pipe, only by the size of the second pipe, because the first pipe can be as big as it wants, but then if this pipe is small, then there will be a bit of bottleneck up here for obvious reasons. Now if you have a bucket again, and then we have a bigger pipe here, and then we have a smaller pipe here, then the bucket will get filled by the first pipe, because however big this pipe can be, the smaller pipe will just give as much as it can to fill the pipe, to fill the bucket. In other words, there will be a simple formula saying that if the transmission or the throughput rate is basically the packet size divided by the packet size divided by the minimum transmission rate between the minimum transmission rate between the rate of the server and the rate of the client. Let me write it better. So the throughput is equals to the file size divided by the minimum of the rate of the server and the rate of the client. This is the throughput, and you need to remember that is very, very, very important. Okay, let me delete that. Now, what is the average end-to-end throughput, right? The average end-to-end throughput will be the RS, right? RS is smaller than RC. What's the average end-to-end throughput? It will be, in this case, RC, because RC is smaller than RS, right? And it makes sense because as big as RS can be in this instance, this computer cannot receive more than what RC can send. Similar to this one, this computer cannot receive more than RS can send, right? So this one is a bottleneck link that constrain the end throughputs. So this RC rate will create a trouble here because it's too small, and it cannot cope with the speed of RS. That is the issue. So it will become a bottleneck. All right. Now, this is the very last page of our course here. We have a network scenario. We have multiple components that are basically ganging up together, and a very big pipe here. You have 10 connection, 10 connect. I mean, we have a couple of connections. They all share a link, right? So by connection, and like the same thing always happen. We will take the minimum of all the RS or all the RS's, and we have also this R, and we divide it by the number of connections, right? So this is in practical part how the data travels from the server to the client. It's very, very, very important for you to know those measures. It's very, very, very important for you to know what can be a bottleneck, why link can be faster than the other one, what are the different transmission medium that can help you to have a faster transmission rate and stuff like that. So this is basically the end of the lecture. As usual, you'll be having a quiz with some questions, and those quiz they count for marks. They are serious one, they'll be counting towards your final mark. Again, I'm wishing you good luck for this particular lecture, and I'll also create some sort of little lecture or video that will show you examples of what we were speaking about through this lecture too. Goodbye.